where will you find resilience? REdeploy.
All right. This is really exciting to be here. I've spoken about this at a couple other places, but no other place has been just a room full of resilience engineers who get to listen to this, and we get to talk about this in a community. And by the way, you're all resilience engineers now. Sorry, there's no take backsies. You're stuck. Once the genie's out of the bottle, there's no going back. This talk, I want to first preface it with the background, very briefly, on where we're coming from. Now, when we talk about resilience engineering, it's a very explicit field we're talking about. And it kind of sounds like, well, we're in software. Engineering seems like it's a core part of what we're doing every day. So that should be like foundational to what we're doing. And it is. But we didn't invent this. It didn't come from us. We've heard it before. This is something we're borrowing from other fields. In medicine, air traffic control, nuclear power plants. This is something that we're borrowing from the fields, and we're trying to apply to what we're learning day to day. A lot of the ways we come into it are through postmortems. I tend to use Retrospective. Feel free to just do a quick mental sub of that too. And that usually means the meeting itself, not necessarily the documents that are produced from it. Sometimes it's partially through chaos engineering experiments. We kind of have some overlap there, or maybe incident management. And so resilience engineering is critical to what we're doing, but it's important that we don't confuse what we mean by that, that we don't have to reinvent the wheel here. We know what we're talking about because other fields have explored this already, and we should tap into that resource. So let's talk about a quick definition of what, at least I'm coming from in my point of view, we mean by resilience. Now, here's a fantastic quote from Dr. Errol Hollnagel. He was in the lunchtime video, Safety Differently, from Decker. And this is a great quote. It's one of many kind of takes on resilience. It's mostly about adaptation and how we're handling things. And there's other different approaches to resilience. There's the Woodsian approach of being dynamic systems and graceful extensibility, which are important and key as well. But I want to focus on this. But what I'll say is this is a lot to remember. It's hard to keep this all in mind when we're trying to look at our systems and explore, is this resilient or not, or is this displaying resilience, I should say. And so I want to reduce it down for this talk to 3 words. When we're talking about something, I'm going to ask, can it adapt? And when I'm asking if it can adapt, I'm looking at, can it make decisions? And this is different from conditional logic. We want to ask, can it change course? When new information comes in, or can it actually keep the same course because it's believing that what we're doing right now is still the right action, despite new information. Or maybe new information is reinforcing that. Can you use any kind of assumptions, hints, clues, any expertise built over time to chart a path forward? And only with keeping this in mind can we say that something is displaying resilience. And so with that, let's talk about our first myth. Myth number 1. We're building resilience into our software and server architecture. This is actually impossible. We can't do this. It's because our servers and our software are predetermined. There's no changing course after the fact. Usually when we say this, we probably mean robustness, maybe reliability in some cases. And what we really want is we want to focus on what are the people parts of the system? How are we focusing on the decision-making properties after the fact? So let's talk about the difference between there, robustness, resilience, and reliability. Robustness. We're talking about this soft boundary on the system we're working in, and can it work within those predetermined boundaries? That's what we mean by robustness. Are we caching static assets on our site so that we're not incurring so much load in particular servers? Are we approaching it with an idea that, well, our databases can fail over to a secondary if some sort of anomalous bug takes it down? Can our load balancers add or remove nodes when it needs to? Because maybe it fails a health check, or we need to extend what kind of services we need to currently employ in production. These are all great, these are fantastic, and we need these in our day-to-day lives, but these are all examples of robustness, not resilience. There's no decision-making happening. Next, I'm going to talk about reliability. And for my approach, I'm looking at this in terms of what is our trust and what is our ability to understand those expected boundaries and whether our systems will handle within it. How are we assessing that boundary? How do we know where that gradual decay of the boundary extends? Where does it start and end? There's no real start and end to that. Like, where do we feel comfortable being within that? What kind of confidence do we have in system safety from where we're existing in? Now, I want us to all put a pin in this because I think this is important to think about, and we're using this a lot. But I think we need to expand on this a lot more as well. Next, I'm going to talk about resilience, which is why we're here. And we're talking about resilience, talking about can it adapt when it goes past that boundary. And some examples of this, do we have someone who goes off script from runbook? Maybe our runbook isn't up to date. Maybe it's not as extensive as we thought it was. It doesn't cover a situation we didn't believe that would happen. That's resilience. That's displaying resilience. Is it an operator who's terminating a rogue process? Maybe you need to reduce load on your servers. And yeah, we're going to lose some functionality of the site, but the greater functionality is needed, and so we need to shed load somewhere. Maybe it's even you're on call, and you need to page someone else because you're just not quite sure how to handle a situation. And you need to bring more people in so that they can think about, okay, how can we, as a group, collectively talk about this, use our shared expertise to move forward, to understand how we're keeping our systems up. So with all this in mind, our servers and our software cannot display resilience. They don't have resilience. But our systems can because people are part of the system. And this is what we need to focus on. How are people day to day keeping our systems up to date? And now you might think like, well, isn't this kind of pedantry? Like, aren't we just splitting hairs here? We really mean the same thing. We want our systems to function. We want it just to work. Reliability, resilience, robustness. Like, why do we need to get so granular about this? And in general, yeah, we can get things functioning without worrying about this. But when we focus on the difference, we can focus on things like, how are people doing day-to-day work? How are we explicitly working on things past just, yep, I am certain this will work, and I don't have to worry about it when it fails. Our chaos engineering experiments, sure, they can do some basic testing, but are we developing any deep insight from them? Our incident management, are we worried about when we're in the thick of it? Are we able to show any kind of flexibility and understand what's going on? And for our retros, are we going to give shallow answers to simple questions? Or are we going to look for deeper insight? And that's what resilience is looking for. Myth number 2. Complexity is the enemy of a well-maintained system. This might seem kind of basic too. Like, don't we want to just approach this with, yeah, okay, let's reduce our complexity. Like, let's make our systems easier. It's going to be a lot easier to function in them. We don't have to worry about things falling over as much. Like, if it's simpler, I can understand it. I know what's going to happen. But sometimes we need to add complexity to our systems. There's a necessity to adding complexity. Our business needs require us to build in complexity into our systems. If you're worried about this, you think, like, well, is that really true? I don't know if that doesn't really make sense in my head. Try this experiment. Take your individual systems, your code bases, take out every line of error handling, observability tools, logging, any kind of failover. Remove all of that. Yeah, our systems are a lot simpler now. They're a lot less complex. But are they going to work the same way? Are you going to feel as confident in your systems? Are you going to feel like, yeah, our code base is better for this. Our system is better for this. So sometimes that little added complexity is going to help you. So the question really isn't always, how do we cope with complexity? Sometimes the question is, the question isn't how do we reduce complexity, it's how do we cope with the complexity that is required for our day-to-day work? And there's two views on this. The first is taking a pessimistic view, that every system in the world goes through this cycle. There's this expansion, we're adding more and more and more complexity, eventually we hit the saturation point, and our systems can no longer handle it anymore, and they collapse. And we kind of throw it away and start again. And this feels somewhat intuitive, especially in software engineering, like we're adding more code, adding more tools, more lines. We need to make sure we're trying to put all these guardrails into place. And finally, it's, I can't take this anymore. I don't know what I'm doing here. Scrap it. Let's build version 2 of this. Let's just start from scratch. But it doesn't have to be this way. And this is what resilience engineering is focusing on. Resilience engineering takes an optimistic view. People are part of the system. People can self-monitor. We can adapt. We can anticipate what's happening before we hit that saturation, before we hit that eventual collapse. We can make minor changes along the way. Now, this is difficult sometimes to build into your system because we don't know what the cost is. We don't know when that uncertainty is going to hit by mere definition of it is uncertain. We don't know which uncertainties we're going to hit. So we have to constantly put in this effort time and again, not having any certainty that it will eventually pay off or that we've got the right answers when problems hit us. That's tough to bring in. But without that constant expertise that we're building in, that learning, that anticipation, we're going to fail again and again, hit that collapse in worse ways. Myth number 3, we need to execute chaos engineering experiments to find the bugs. Now, I want to come at this with the right approach, saying that chaos engineering is not equivalent to resilience engineering. There's overlap. There's definitely adjacency there. We can do some good stuff with chaos engineering that doesn't exactly fall within the vein of resilience engineering. But there's a lot of good we can do that has that overlap. And so when we expand that, when we focus on chaos engineering butted with resilience engineering, there's a lot more we can take from it. There's a lot more we can learn from it. Chaos engineering is about developing intuition on top of just seeing what goes wrong. What kind of mental map do we have of our system? How does that mental map, how does that model of what we're looking at map currently to what our system is displaying? How is that system changing while our mental model stays static? How do we keep updating that mental model? Some of that anticipation, some of that learning is coming from chaos engineering, and we need to focus on that. That's the good part, that overlap we need to look at. Myth number 4, always follow best practices to ensure system availability. Now, systems fail for all sorts of reasons, even when we do the right thing. And so when we're talking about best practices, it's like, well, why wouldn't we follow best practices? I mean, they're best practices. They're the best. That's why we call them that. But it might not be a fit for your situation. We can say, okay, well, I read it in a blog post, I heard it in a conference talk. We got to try it here. I mean, they told us we need to do it. So what happens when we apply a best practice and it doesn't work out? Deploy on a Friday. And a chill goes through the room. Now, some folks might say, sure, always deploy on Fridays. That's best practices. You need to deploy on Fridays. Some folks say, whoa, 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 slow down. You don't deploy on Fridays. It's a Friday. You never, ever, ever deploy on a Friday. Unless, well, okay, there's a security bug. I mean, we got to fix that. Like, we can't just leave that over the weekend. We might get hit with this major vulnerability in our system. Or, well, there's this test I really want to run over the weekend, and I need that data, and there's going to be some interesting traffic that comes through that I want to capture through that. Or maybe there's a launch that happens on a Saturday morning, and I need to have this deploy out there so it's ready for that launch. There's all sorts of reasons we can come up with where we might need to deploy on a Friday. And so, what do we do when they're opposing best practices? And that's the problem with best practice right there as a term. Best practices do not guarantee safe actions. There's no guarantee that when we do something that's called a best practice, that things will stay up and we'll do the right decision. We're removing all that nuance, that thinking, that important utilizing of our expertise when we rely on blanket statements like best practices. On top of that, a lot of times Best practices are ways of justifying things after the fact. For example, say I make a change, and I'm going forward, I'm ready to deploy to production, and best practice might be, okay, well, you always wait for tests to finish before deploying to production. Always? I mean, it's a best practice. Should we always do that? What if the site is currently down? Do we wait for tests? Say the tests take 10 minutes. Do we wait an extra 10 minutes while the site is down to make sure, yep, the tests work? Maybe. We should understand the situation. We should understand the problem. Was it a quote-unquote simple rollback or revert? Maybe we should wait. And this is what we're lacking when we say always rely on best practices. My thinking around this are we should just remove the term best practice altogether. Maybe industry standards, that's a decent alternative. It indicates that, yeah, this is what most of the people are doing. This is what we generally rely on. But it's not going to guarantee that things will work out. So use your best judgment on top of this. Myth number 5. Effective retrospectives require Aximal follow-up items. I see this a lot with systems or companies that rely on templates for their retrospectives. Here's the time it started, here's the time it ended, here's the severity. And here's what we make sure that we accomplished. Here's everything we're going to do after the fact, so make sure this doesn't happen again. And we understand this. Like there's a sense of control. Like we got hit with this major bug. Oh, it's so much stress. Our business took a hit from this. We're going through comms and fighting fires. Really so, we don't want this to happen again. And so there's this comfort, there's this warm blanket of we're going to have the tickets. We're going to write up Jira or Trello tickets, and then it's never going to happen again. Fantastic. But failures have a fun way of routing around our best efforts. These Jira tickets that are going to solve all our problems don't guarantee that the failures won't happen in a slightly different way again. Now, if we're not using Jira tickets, if we're not using any kind of follow action items, how do we know our retrospectives are actually worth the time? We're spending all this energy, we're interviewing people, we're putting together this timeline, we're getting all these folks into a room. By the way, it doesn't have to be engineers. Non-engineers should be in retrospectives. And we're putting together this document, and we're asking all these questions, and then what? How do we know all this effort was worth it? And this is a really difficult question to answer. Because what we're really asking is, how do we know we learned something? And we can't guarantee that people learn something in a retrospective. We can try our best to do so, but it doesn't mean that it's guaranteed. For my sake, I too believe that when we walk out of a retrospective, we should understand, do we feel like our engineers are more confident in their systems? Do they have a better understanding? Were there surprises and they learned something? Oh, okay, now I know this. I figured out something, TIL, right? But you could also apply, well, thinking around maybe, say, a conference. I mean, we're all here attending, right? Our companies flew us out here. They bought us tickets for the conference. We have per diems, possibly for food, hotel stay, away from desk when we're doing other work. Where are the actionable items for a conference? How do we know this conference is going to guarantee learning? We don't have any solid we don't have, here's the Jira ticket. I learned 10% more. I'm 10% better an engineer because I went to this conference. But we all believe, we come out of this, we say, I learned something today. Here's what I can share. Here's the expertise I feel like I've built up as part of this. There's an inherent belief that we come here, we can learn, and then spread that information around. I think we should apply that same logic to our retrospectives. Myth number 6, root cause. Woo! This is the seventh inning stretch of the talk. Yeah, I'm fairly confident that most of the people here have either heard of root cause being a myth, believe it, at least have an inkling towards that direction, maybe even got into a nice Twitter argument with someone saying, no, root cause doesn't exist. And so my goal here today isn't to convince all of you that root cause is a fallacy. My goal is we should build up an understanding why we say this. We shouldn't just repeat it because we say root cause is a fallacy, period. We need to convince other people. That's the trick. We need to have a deeper understanding, and that's where some of that learning comes in too. How do I explain this to someone else, that root cause is a fallacy? I'm also seeing this a lot in a lot of retros out there, postmortems, that say, here's the root cause of the problem, we fix this problem, everything's better. So what is the problem with calling something a root cause and saying, why is that a fallacy? It's because a lot of times when we use root cause, there's a lot of shallow thinking. We want a simple answer to things. We expended so much energy just fighting the fire and getting out of it and getting back to a stable state. We want this comfort of, how do we just explain this away in an easy way that I can understand and move on and get more things done? But that leads to shallow answers. We don't have a deeper understanding when we say that. A lot of times when we use root cause, it tends to fall in the most politically expedient way, and someone who we can be okay, we're just going to blame this engineer and that's it. But there's more to it than that. I also see people using 5 whys as part of their retrospectives, sometimes RCA or root cause analysis. And this is equally fallacious. This is the same idea that there's this idea of linear causality in everything we do. Event A happens, and then B follows A, and then C follows A. C is where everything blew up. So if we just remove A, B and C won't happen, and everything will be fine. But that's not how things work. A lot of times, many things contribute at the same time to produce a failure state. In fact, there are multiple failures happening all the time that don't escalate and don't cascade into this larger failure. And that's what root cause ignores. If you use 5 whys, you might ask a team, everyone give your separate answers to 5 whys why something went wrong. And you will get different answers from every member of that team. Were they all existing in different parallel universes to come together? No, they all shared the same timeline, but they all have different perspectives. And 5 whys fails to acknowledge that. You also might say, what's the root cause of, say, success? What's the one thing that happened that made something go right? And there isn't. Many, many things contributed to that. That same kind of logic should be applied to failure. So if we're looking for a nice substitute, I tend to use contributing factors. Maybe not quite as pithy. It's a couple more syllables to eke out. But it acknowledges all of that underlying problems. Yes, there might be more things we didn't uncover with this. We need to stop at some point. There is a limit to how much until we get to the Big Bang. We can't start there every time. It also acknowledges things like emergent phenomena. Things happen, our new knowledge surfaces as we're exploring, as we're understanding our situation. Myth number 7. The frequency and severity of incidents are good indicators of how safe we are. This is often paired up with when people use MTTR, mean time to recovery, or MTBF, mean time between failures, as indications of, yep, we haven't had a major outage in 60 days. We must be doing something right. No failures. Good job, everyone. Again, a nice, comforting, warm blanket to snuggle up to because, well, it's the numbers. They don't lie. They're numbers. You can't fake numbers. But this also fails to acknowledge that failures are constantly happening. These are just the failures we're acknowledging. These are the failures we're counting. Failures are constantly happening because we just don't worry about some of them. It also ignores the fact that there's this concept of dark debt, some of you may have heard of. Normally when we make a decision about a technical problem, we take on technical debt. We've heard that term before, most of us. The idea that, yes, we're going to have to pay something down the road. We have to rework this later. We have to reshape this module. Sure, I understand that cost, but there are hidden costs we don't understand with that decision. And they might bite us later on, ticking time bombs that exist in our systems. How do we face that? When we look at MTTR and MTBF, they're ignoring that. And numbers can be really easily gamed. Using things like severity, too, on top of incidents. Well, okay, I'm hoping for a promotion this quarter. And yeah, we had that Sev 1 last week. Maybe that gets bumped down to a Sev 2. because I want to look like I'm doing a good job. I want to make sure that they think I'm keeping the system safe. Or vice versa. Hey, this Sev 2, I'm going to bump it up to a Sev 1 because I need some headcount, and I need to let upper management know I'm having problems, and I need more people to help solve these problems. And so all sorts of fun ways to play with those numbers. Who recognizes these logos? Quick show of hands. I won't ask you to explain it, but I'll say maybe 25%, a little less maybe. Cool. So these are the logos for two vulnerabilities, the Meltdown and Spectre ones. I'm going to hand wave them a bit and combine them. The idea was that these vulnerabilities, when they showed up, I think it was last year, there was an exploit with hardware speculative execution of code. And you could, if you manipulated it right, read memory of a process that you didn't own. That's a nasty vulnerability. You could pull in some really sensitive data if you managed to get access to a server. That code was written not last year, not the year before, or even 5 years before. The code was written in the 90s. Some of that code was 25 years old. I mean, it went through QA. It was written by smart engineers. They did the tests. They put it through production. How many thousands, millions of hours of production execution of that code exists on countless servers? Over 25 years. There might be some people in this room who weren't alive when that code was written. This is a scary thought to me, that there could be code that is 25 years old that might still have vulnerabilities. I don't have code that's maybe 5 years old, 10 years old, that I could say, yeah, without a doubt, this is going to work 100% of the time, says absolutely no vulnerabilities in it. That's a scary thing to think about. When do we know our code is safe? How long should it last in production until we say, this is right code, it's working as is, there are absolutely no problems with it? And so when we're playing with this, I like to say we should, instead of sharing numbers to highlight how safe we feel about this, it should be, what's our confidence in our system? Ask the obvious questions, and obvious should be in heavy, heavy quotes. Talk to the experts in your companies, in your systems. What do they think are the big problems with their systems? What do they think are the safe places to look at? And what should they still take a look, even if they think things might be safe? People who have the most expertise in those systems. That's how you understand risk. That's how you understand how safe do you feel doing the day-to-day work. Myth number 8. Our worst incidents produce the greatest learning experiences. This can be fun. We always like to hear about really major outages, you know. AWS goes down in a whole region and the internet freaks out. And those are fun to listen to. Like, of course, it had to be something fun. Something truly outstanding must have happened for something so big to affect so many people. But that's not necessarily the case. That's outcome bias. Simple failures can produce large outcomes, or a combination of simple failures can produce large outcomes. Severity is not correlated with learning. Just because something bad happens in a large way doesn't mean you're going to learn a lot. Sometimes it can, and we like to cite things like, hey, Knight Capital, how many hundreds of millions do they lose in X number of minutes? That's a problem. And there's stuff to learn there. But we can also learn from smaller incidents as well. And even in the most blame-aware companies, this can be a problem. If we're looking at really major outages, I don't want to blame Sue. She's doing a great job day in and day out, and she had an understanding of the situation, and it was incorrect, and I want to back her. I don't want to throw her under the bus. Maybe I start using some passive language. Maybe I try to smooth out some edges during the timeline so that it doesn't feel like she is getting thrown under the bus. And that's not always great either. We want to hear about those close calls, those really major outages, and everything in between. And so when we smooth out those edges, that's learning lost. That's things we're missing. So instead of always focusing on how things go wrong in the worst possible ways, look to close calls. On top of that, look at situations where your experts were about to hit a button and go, wait a minute, should I really run that SQL query? Let me go check with the DBAs. Oh, we haven't indexed that table. That query would have taken 3 hours and locked up the entire table. That could be bad. There's a lot of learning to be had there. Why did the expert pause? Why did they think, maybe I should ask someone else first? What gave them that moment of hesitation? I need to get confirmation here. There's a lot of learning to be had from that as well. Myth number 9, error budgets can be used to control risk. Now, I've talked about this with a room of SREs, and they didn't tar and feather me, so I feel confident I can say this here. I know there might be SREs here. I'm actually on a team of SREs. And I will state, for the record, I'm not a huge fan of error budgets. Quick summation. Actually, show of hands. Again, who knows what error budgets are and how to use them? All right, I'm guessing like 75%, maybe 80% of the room. I will give a quick recap because I want to make sure that we all feel like we have a general grasp of this. Error budgets. You start out with your SLI. It's your service level indicator. It's a metric you use to gauge user happiness in general. I'm going to hand wave a little bit here. And from that, you set a service level objective. You might say, what's your uptime for your service? How many failures are you getting in a certain period? That objective is maybe say like 4 nines, for example. And if we dip below that, we've expended our error budget. If we're above that, we have a little bit more error budget to use. And we have our service level agreement, what happens when we dip below that line. And how do we apply that error budget to our current roadmap, to our current working system? A story. An engineer starts at a company. They're a senior engineer. People are enthused about them starting. As part of that onboarding process, they do a sort of boot camp. They kind of rotate between teams. They might do a quick task here and there. They're trying to learn how other teams are working within the company. A part of one boot camp, one session, they are tasked with cleaning up some files. It's a simple fix, just delete some files, check it, push it to production, get an idea of how to deploy to production, how this team is doing their day-to-day job. Great. They delete a file. They run the test pass. They get peer review, thumbs up. They go to deploy it. They push it to staging environment. There are other senior engineers who have been at the company a while who are looking to change. They inspect the site. Things are looking great. They go to production. 2 minutes later, site down. Patchy nodes are just falling over. They're getting locked up. Child processes are just getting held up. No one can figure out why. Ops team is rushing in, trying to reboot servers left and right, and they just keep falling over themselves. As a means of trying to return to stability, they decide to revert the change, revert all the changes in that latest deploy. Ops does another reboot across the fleet, site stays up. Let's look through our change set. Okay, we see this change here, we see this change here. We get the senior engineer. That seems a pretty easy fix. I mean, that's a simple change. I mean, they deleted a CSS file. No way you can take down a site with a CSS file, right? I mean, it's CSS. Worse, you see like a little jankiness on the site. Oh, it didn't load my textures or whatever. And then with a little deeper, and a little deeper. And we said, okay, well, while this outage is happening, I'm seeing a lot of 404s, way higher than normal. Where's this CSS file used? Well, it's part of our static asset building, and CSS file is used as part of the 404 page. And we weren't testing 404 pages locally. So when we get to production, naturally, we hit a 404 page. We try to fetch the associated page for that, our natural 404 page. But it doesn't exist. Static asset never built it. So what happens when you try to fetch a page and it doesn't exist? Well, better issue a 404. And that one doesn't exist. And so every time a child process came up and needed to serve a 404 page, it would get locked up waiting for the next 404 page to get served up. Where was the risk in this? Where did they fail to see this was a risky change to make? And that's what error budgets are failing. They're looking at past experiences to plan future actions, past failures. Error budgets take a very safety one approach. Look at the failures, see what's going wrong, fix them, move on. But resilience engineering takes a safety two approach. Yes, look at the failures. Those are important to look at. But on top of that, also look at what goes right. What are the close calls? What are the experts doing day to day to make sure things go right? The idea is we don't know a lot about risk when we're counting errors. We don't know what a risky action is that happened yesterday necessarily informing the next one, or what even is a risky action. You don't get that from error budgets. I don't want to tell anyone, if you're using error budgets, stop using it today. There are great teams out there who are doing great work, and they use error budgets, and I would say continue doing that. But understand that error budgets are not going to inform you how risky your changes are. Myth number 10, and this is our final one. The field of resilience engineering is representative for the study of human factors. Chances are, if you hear about resilience engineering from someone, especially on stage, they probably look like me. They're probably white, tend to be male, tend to be from North America, maybe they're able-bodied. There's folks in non-software industry that are coming from Europe that are talking about this as well, which is great. But we're not hearing from everyone. There are plenty of people in the industry who are not participating. We need to get them part of this. That sucks. And I'm including you all now because you're all resilience engineers, we need to do better about this. We need to bring in voices from underrepresented communities. That's how we're going to get better. We need their expertise. We need to focus on that. Where are we not reaching out to? So I've talked about all these myths before, and I want to highlight a few extra things on top of that as part of REdeploy, because we're here to discuss these things. These aren't solved problems. We haven't figured out everything. There's so much more we can learn to get better at. We're just scratching the surface as we bring it into the software industry. And so I want us to think about a few things on top of that. So earlier I mentioned I'm going to put a pin in reliability. I'm going to unpin it now. I don't think we've got a great grasp of reliability. I think we're being a little hand-wave with it. Which is weird because a major philosophy in tech right now is SRE, Site Reliability Engineering. But if you ask several people what reliability really means, you're probably going to get a couple different answers. And there's some ideas around this that are really interesting about mass-produced products and what their guarantees are. When you put them through the works, what are our expectations and how many times, for example, hard disks. And say, hard disk, after X number of reads and writes, you're probably going to start getting failures. But code doesn't work that way. We're doing a lot of custom stuff every day. We're not doing the same things in and out. It might feel like it sometimes. We're doing a deploy, but those deploys are always having little subtleties in them. They're not mass-produced. I'm toying with the idea right now, and I'd love for us to discuss this more. I'd love pushback. I'd love thinking around this. I believe that it requires more thinking around this. It requires more understanding when we say something is reliable, or has reliability. I think it requires more than just mass-producing code. We have to have confidence in what we're doing to really consider something reliable. Next, what does it mean to learn? I am very fortunate to have married a smart woman. My wife, Dr. Teresa Damaro, she got a doctorate at NYU in biology, studying molecular oncology. So she's very, very smart and much smarter than me, and I'm appreciative of that fact. She also studies pedagogical research. So she's learning about learning. And so I love to talk to her about, hey, we have this retrospective, and here's what we said, and we go into the timeline. She's like, that's great, but it sounds like you got up there, Will, and someone walked through a timeline, and they read through a document, and everyone nodded, and then walked out the room. What does that mean for learning? How much effort are we putting into these retrospective documents that we never come back to? Are we pulling it up a week later, a warm cup of coffee, and just reading over a retrospective document? Not necessarily. I bet it's pretty rare, even in the best case scenarios. How do we know we're learning after a retrospective, after an incident? I don't want us to start testing people or quizzing people. I think that's an off way to go about it. But I think maybe an inquiry-based model for our learning might be really interesting to tap into. How are we developing durable knowledge, which is going to be foundational for that expertise that is so necessary for resilience engineering? And lastly, I want to talk about making intro to resilience engineering a bit more welcoming. I think it's really hard to get into this. I think there's PDFs and books and documents and conference talks to listen to. How do we get through all of that? How do we understand everything we need to know just to start? I think we need to make it a little more of a gradual slope to get into this. What are the basic things we need to know? What are the learning steps, the 101s for resilience engineering? With that, a quick couple takeaways. First, these are 3 resources I'm sure most of us have seen, but I also don't want to assume anything. I'm a big fan, of course, of Dr. Richard Cook. Spoke to us this morning. Thank you again. If you haven't read How Complex Systems Fail, I know we've already mentioned it once today. I'm going to repeat it because it's 4 pages. You can find it online for free. It's a couple of bullet points, and it'll blow your mind at how much it lines up with your thinking. The first one at the top is the Edo Principle. It's a book by Dr. Eric Hollnagel, the efficiency thoroughness trade-off principle. I think gives a lot of insight into how we go through our decision-making process. And finally, the Field Guide to Understanding Human Error by Dr. Sidney Dekker. I consider that required reading for anyone holding retrospectives. We can't plan for everything. Things are going to happen that are unexpected. Those are surprises. That's why we have incidents. So we need to understand what we're going to do when the unexpected hits us. We need to get experts to share their expertise, even asking what are seemingly obvious questions. They don't necessarily know that they need to share information. We shouldn't hold back on asking those questions. How did you know to do something? And finally, embrace uncertainty. Things are scary. They're going to keep being scary. But if we don't prepare for this, if we don't start trying to add to our expertise, to get flexible to adapt to situations, we're going to crash and burn. Thank you all very much. I've had fun talking to you, and I look forward to talking to you later today.